Hello, this is Dr. Strickland. In this video, we will finish our investigation of reaction coordinate diagrams. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. All right, so we have done the reaction coordinate diagrams for the two different steps of the reaction between 2-butene and HBr. And when we did that, then we called this Q, and this ultimately was T, just using some letters to represent structures to make our reaction coordinate diagrams a little simpler. So we'll continue to use that there, and I would invite you to refer back to the video and your notes that came right before this. So we know that the Q was, let's say here, this was the 2-butene plus the HBr. And we know that in the first step, we broke a couple bonds, we formed a bond, and overall, there was more energy consumed than released. So the intermediates were less stable. This is P, that was the carbocation intermediate, plus the bromide ion. And then the two of them had a reaction, and we formed one bond. So when bonds are formed, energy is released. So this step is exergonic, and so that's where we find the final products. So P is an intermediate. Okay, so this guy here, because it's formed in one step, and then it's a reactant in the next step. Now, this is reaction 1, and this is reaction 2. Well, step 1 and step 2, because we put in the free energy of activation for each step. So it looks something like that for step 1. And you can see that the free energy of activation for step 1 is a lot larger than for step 2, at least in the forward direction. Okay, and we also talked about the transition state for each one, and we gave them letters too. This one was R and this one was S. So the structure at the top of each of these energy hills, it's an energy maximum. These are transition states. And each step in a mechanism has its own transition state. And when you look at an overall, the total of all the steps of a mechanism, you'll have the number of steps is one more than the number of intermediates, because the product of the second step is the final product. Okay, so, and then I'm just going to put the free energy change for the entire reaction. Between the original reactants and the final products is always the difference in energy between here, where the original reactants are, and here, where the final products are. Doesn't have anything to do with what's going on up here. All right, so I want you to assess one for me. Here's a different one. Take a look at this free energy diagram and the questions that come with it. So this is a 3-step mechanism. I know it's 3 steps because it's got 3 energy maximum. Okay, so I want you to pause the video and answer these questions. How many transition states do you see? And then tell me the letters that represent them. Which step has the greatest free energy of activation in the forward direction? How many intermediates are there? And tell me their letters. Is the first formed intermediate more likely to revert to reactants or go on to form products? And then finally, what is the rate limiting step? All right, so pause the video and do those, and then come on back. All right, welcome back. How many transition states are there? Well, they're the things that come at the top of each hill. That's the energy maximum for each step. So there are 3 of them. And they're represented by B, D, and F in this case. Which step has the greatest free energy of activation in the forward direction? Okay, so when you're doing free energies of activations, I would invite you to do this in pencil, because if in the list you have to do something in the reverse reaction, in the reverse direction, you might want to be able to erase all this. So this is the free energy of activation for the first step, going from left to right. For the second step, going from left to right. And then for the third step. All right, so which step has the greatest free energy of activation in the forward direction? Well, I think it's the second step. So you can answer this question, like step 2. Or you can tell me what was the reactant and what's the product of that step. So this is C to E. All right, how many intermediates are there? Well, an intermediate is an energy minimum in between the original reactants and final products. So that one and this one. So there are 2, C and E. All right, is the first formed intermediate more likely to revert to reactants or go on to form products? Okay, so let's talk about this free energy of activation thing. This is something up at the top of the page. Come on back up here a minute. Okay, so in a multi-step mechanism, the rate limiting step, which is also called the rate determining step, is the slowest step. And the slowest step will have the largest free energy of activation. Also, the reason it's important is because the rate of the slowest step is the major factor in determining the rate of the entire reaction. All right, so just while we're here, let's do number 5 and then come back to number 4. And let's say, what is the rate limiting step in the forward direction? Because it might be different in the reverse direction. Okay, so the rate limiting step will have the largest free energy of activation. So again, that's step 2. So the fastest step actually will be the one with the smallest free energy of activation. All right, so now let's go back to number 4. Is the first formed intermediate more likely to revert to reactants or go on to form products? Okay, so now we're talking about C. And we want to know, is it more likely to go left to right or more likely to go right to left? So so we can focus on that, I'm going to take out the stuff we were doing with step 3. And I'm going to take out this because we want to know about the possibilities going forward and going backwards from C. So let's make this, give us a subscript of F for forward. If it's going C to E, this is the free energy of activation. If it's going from C to A, now we need the reverse. So the one that's more likely to happen is the one that has the smaller free energy of activation. So it's more likely to revert to reactants, which would give you C to A and not C to E. See that? All right. So that is the story on reaction coordinate diagrams for multi-step mechanisms. If you have any questions, please send them to me.